All right, this video is to work through a few of the demonstrate understanding questions and the practice just to show a little bit of how I think about these problems and hopefully help someone in class learn how to write the equation for linear and exponential functions a little bit more. I am about to move my laptop so that it's easier to write on. And so I'm going to stop the video from my end so that you just can't see me, but the focus is on the solution work. All right. So I'm going to work through these a little bit quicker, but these are the demonstrate understanding questions. This first one here, remember my recommendation is to identify the type of function right away. We see a line on the graph. So this is a linear function because the graph shows a line. I am intentional about not using the word it. I am not talking about a constant additive rate of change yet because I have not found that yet, right? Why? The reason I know this is a linear function is because the graph shows a line. Immediately after that, my equation I know is going to be mx plus b. There's a few different ways to show the equation, but this is the one that is most traditional and students are most used to. And now because I have that, I know, man, I need to find my slope. Identify any two clear points on the graph. I am noting those here. And I see that I am rising 3, so up 3, and I am running to the right 4. So my slope, my change in y, right? So don't forget that Greek letter delta. It just means change. Change in y is 3. Change in x is 4. I do want to note that if you were to have changed it from any 2 points, that does not change anything about the slope. This time I am rising 6 and running to the right 8. And if I take 6 and I divide it by 8, that still is 3/4. I could even go backwards and go from this point up here on the top right, that 0.2 or 8.2, I believe it is. And it would go down to 3 and to the left 4. And still, -3 divided by -4 is equal to 3/4. Don't forget, you can make it into a table. Any option, change in y divided by change in x. That does not change from 3/4. Now I need that b. That b is my y-intercept. And I can see that easily on the graph right here on the y-axis as the point 0, -4. Make sure you remember y-intercepts are in fact points, not just a single number. Once we put it into the equation, though, it is the single value, -4, the y value of the y-intercept. And now I'm done with my equation. I have evidence all over the place because I am always trying to justify my answers. In a similar way, when I look at number 2, I'm start thinking about, hey, what type of function is this? Right? It's got a table. When I see a table, I'm thinking about rates of change. And so some might be tempted to say, hey, -8, -4, -2, -1, and okay, that's +4, +2, +1, but I see nothing constant in the additive portion of this function. So I am not thinking about additive rates of change. I am now thinking about multiplicative. You might notice divided by 2. And so if you notice divided by 2, it's just the same as multiplying by 1/2, which will be helpful for the equation. If you're not seeing that times 1/2, that 8 is quite literally half of 16. And don't forget, I am moving this direction in the x because I always read a graph just like I read a book from left to right. So -3 is the leftmost x value, 1 is the rightmost. And so if you don't know what your constant factor is, remember that's the name of the multiplicative rate of change, or the constant multiplicative rate of change. Now, based on this, I can write an equation. 16 times my constant factor is equal to 8. And then I can solve this equation using my inverses. I like to use that reciprocal to show the division by 16. 16 divided by 16 is 1. And I am left with 1f is equal to 1/2. Right? 8/16 is 1/2. And if you check again the rest, and so I mentioned that 1/2 earlier, I'm going to go in and erase the constant f. And 16 times a half is 8. 8 times 1/2 is 4. 4 times 1/2 is 2, etc. And so I see that this is an exponential function because I did it off of a table. I don't see an exponential curve because I see a constant factor. I'm using the evidence that is there. So exponential function because of a constant factor of 1/2. Equation then, right? As soon as I see that it's a constant or an exponential function with a constant factor, a times b to the x, you can label these things to help give evidence of understanding. Hey, that's my y-intercept. That's going to help you identify features. That b, right, is my constant factor because I'm starting at some y-intercept and then I'm repeatedly multiplying for an exponential function. And I can see my y-intercept right here. Remember, to be a y-intercept, it's where the function or graph intersects the y-axis. And every point on the y-axis has an x value of 0. And that's how I can easily see this one. Notice you can create a quick graph if you want as well. And when you create this graph, which I could have done a better job scaling and creating it, but we also see that exponential curve. But I also see that y-intercept of 0 too. So the y-intercept is 2. And we already found that constant factor of 1/2 raised to the x. Done with my equation. Generally, when I look at a table, I always think about the rate of change first. I think about an additive rate of change. Remember, moving left to right in terms of the x values. Well, x is only left to right. I see my y is subtracting by 5 every time. I see my x is adding by 2 every time. So I see a constant additive rate of change. So type of function, linear, because of a constant additive rate of change. Don't forget that is called my slope, right? Change in y divided by change in x. So -5 divided by 2. And that's going to make my job way easier in writing my equation. I know that I need mx plus b. I just identified my slope as -5/2. And b is my y-intercept. And we just talked about the fact that a y-intercept is where the x value is 0. I could make a graph and draw the line, but if I just continue my function in this direction, I get to a y value of 0 right there, or an x value of 0. Do note this value of -2, 0 is not a y-intercept. That is an x-intercept. If you were to graph this, -2, 0 is right there. Not a y-intercept, that's an x-intercept. The y-intercept would be here at 0, -5. And once again, linear if you graph some more points. So there's my y-intercept. So my equation is -5/2 x minus 5. Do not forget to use your equation. That's why I write out that formula right away. Use that equation to help you think through exactly what the equation is going to be, how you're going to find your slope, how you're going to find your y-intercept. Type of function in number 4, right? Moving on, because time is something I've got to be aware of. I've got an exponential function. I'm not talking about rate of change yet unless I've already found it with some evidence. I know it's an exponential function because the graph is an exponential curve. And so when I look at this exponential curve, I now need to write my formula, a times b to the x. I can see that a, that y-intercept right away, intersecting the y-axis. So that a is 2. But now I still need my constant factor. Remember, rates of change are easiest to see in a table, and I never, ever have to leave a function as a graph. 0, 2, 1, 6 is this point right here. And then I've got 2, 18. One of the most common mistakes students make is they try to look at the slope, right? Rising 4 and then running 1. But notice if you look at the next points, right? It's adding 12 and running 1, right? I can't look at slope because this is not a linear function. Slope is a constant additive rate of change. I know it's exponential, so it's got to be constant multiplicative. You can follow the same pattern as before to find that constant factor, but hopefully you notice 2 times 3 is 6. 6 times 3 is 18. Notice that point down here is -1, but it is not 1. It's a little bit below 1. It is actually 2/3 because 2/3 times 3 is 2. But now I have everything I need for my equation. F of x equals 2 times 3 to the x. Done. Writing out evidence, right? I will say this is not what I would consider a CCC plus. When you're talking about evidence for understanding, you got to go above and beyond and add extra details, but that's clear, consistent, and convincing evidence of understanding right here. So number 5, we would want to notice, man, this looks a whole lot like mx plus b, just backwards. And so I can use a commutative property that I've talked about in class to rewrite this as -2/3 x minus 2. Remember, multiplication, the multiplication between -2/3 and x is that defining characteristic for a constant additive rate of change. And so you can, what I would probably do for my slope is I would see that as a change in y divided by a change in x. And from that, I can create a table, right? 0, -2 is my y-intercept, and I am subtracting 2 from the y as I add 3 to the x. And I can keep that going to get several points. I can even go backwards if I so desire and get these points as well. One thing I would remind you of is you can always just substitute inputs in to get outputs out. Input of x, output of y. So like if I look at f of 3, that is -2 minus 2/3 times 3. F of 3 is equal to -2 minus 2 or -4, just like right here, because these are equivalent functions, equivalent representations, same inputs mapped to the same outputs. I can use the table now to make a graph, or I could have made a graph to create the table, right? Y-intercept of -2. Slope of -2/3 is down 2 to the right 3. Notice that matches again, 3, -4, down 2 to the right 3. And so I can go down 2 to the right 3, or I could have gone up 2 and to the left 3 because 2 divided by -3 is equivalent to, or is equal to, you can say equivalent as well, -2 divided by 3. And so now I have a linear function. Boom. Notice I could have made that graph and just converted it to a table. Order does not matter. Now, number 6, hopefully we recognize that exponential equation, a times b to the x. Looking at that exponential there, right? I've got a y-intercept of 0, 6. And I can use that constant factor if I so desire. Exponential, we typically go by ones in the x. We may get a chance to talk about y later, but I'm not worried about changing y divided by changing x. But 6 times 2/3 gives me 4. 4 times 2/3 gives me 8/3. And I could even go backwards. I would have to divide by 2/3 or multiply by 3/2 in that case. And so I get 9 and 27/2. Right. You can check all of these things. G of x is equal to, or G of, let's try the -1, is equal to 6 times 2/3 to the -1. And so remember, we talked about this recently in class, that a positive exponent indicates repeated multiplication. So a negative exponent indicates repeated division. So when I was dividing by 3, now I multiply by 3. When I was multiplying by 2, I now divide by 2. And 6 divided by 2 is 3. 3 times 3 is 9. Just like I indicated earlier. To fit this onto a graph, scaled by 2's. So -1, 9. And notice how I would personally create a table first with exponential, but all I need to do is now take that table and convert or graph those points. 1, 4, 2, 8/3. And when I am trying to do 8/3, I'm just going to scale it, or I'm going to estimate it's a little over 2. And that almost looks linear, but I know this is an exponential function, so I know that it's going to curve and flatten out, and it's going to approach that x-axis. We'll talk more about what's called an asymptote later in this year, and that's the demonstrate your understanding. That should hopefully carry you into a lot of the ideas for the practice. Let me move this so I can actually access this detail. Sorry, my computer is not playing nice. That's a bummer. Now I got to go through and open. Nope. Those are slides. That's what I want. Okay. So a lot of the students don't particularly love numbers 1 through 3. So I'm just going to talk through some details here. I have told you that these equations are correct. What I'm trying to get you to do on numbers 1 through 3 is explain why these equations are correct. So like when I look at number 1, I can very clearly see it's exponential, right? So at least a times b to the x makes sense. But I'm not just asking you, hey, it's exponential. I want us to recognize, hey, my y-intercept is 6. So that 6 is correct. We need to look at the rest of the function. I need to look at the constant factor. Can't see a constant factor easily in a graph. You can, but it's significantly easier to look at it this way. And now I want to recognize 18 times 1/3, 6 times 1/3 gives me the next value. So there's my constant factor, and that's why this is here. With number 2, right? -6, -6, -6, -6, -8. And so you may be like, Mr. Kinney, I don't see that 3/4 there. It's okay, because it's still there. I know this is linear. It's constant additive. And I know my constant additive rate of change is called my slope, my change in y divided by my change in x. And that would equal -6 divided by -8, which is equal to 3/4 when I simplify. And there's my 3/4. I was a little foolish in not leaving myself space here, but if I continue subtracting 8 in the x, I get 8. If I subtract 8 again, I get 0. Subtract 6 again in the y, I get -6 and -12. There is my -12 for that y-intercept. And you go let a student in really quickly, but I'm going to continue this in a second. All right, number 8 here. This one causes students a lot of trouble, but it's exponential. We want to recognize that if it's exponential, I have a constant factor at play. Can only use points that I can clearly see. I can't clearly see and know these, right? So I'm not going to use those. But I can clearly see -1, 100 and 0, 80. And so because I know it's exponential, I know even with just 2 points that are right next to each other, I've got a constant factor. And so 100 times f is equal to 80. Divide by 100. Boom. And then I can clearly see my y-intercept there. And so I didn't go through all the steps that I should show, but I know it's exponential. I would write that out. I would explain it. I can clearly see that my y-intercept is 80 and my constant factor is 4/5. And that's how I got the equation that is on the answer sheet. Okay. Because we did not get to number 11 very much in many classes, I'm going to talk about this one. We would want to notice this is a function. One input is mapping to only one output, but when I look at my rate of change, I have a constant additive right here. Well, based on our conversations in class, because that's constant additive, this rate of change, remember, what has a constant additive rate of change? A linear, but that's not a linear function. It's a linear additive rate of change. And because it's a linear additive rate of change, I know that this is a quadratic function. So I'm not writing an equation for this, not yet. We are going to learn in the next couple of days how to use these x-intercepts right here to write an equation. What I would point out with the rest of these down here is making a table can be very helpful. Tortoise only got 2 meters in a minute, but then started to pick up steam and tripled his distance every minute, repeatedly multiplying by 3. Okay, and so we can make a table, time, distance, 1 minute in, he's got 2 meters, 2 minutes in, 6, 3 meters in, 18, and I still need my y-intercept, so I've got to go backwards and it'd be 2/3. You can make an equation off of that, right? 2/3 times 3 to the x. We're adding here in number 13, 2 gallons every minute. That's repeated addition. And that's also going to be my slope. You can make a table to verify this. But starting value of is my y-intercept, repeated addition by 2, constant additive rate of change. Last one that I'm going to talk about here, actually, I'm going to talk about a couple more. You have 50 M&Ms and you want to make the largest parallelogram possible with the candy. If you're talking about area, you should think about gold rush. When we talk about area, it's equal to some number of units times some number of units. And so we're talking about units squared, that squared indicating quadratic. So you can play with it. You don't have to. Okay. Last couple of things I want to leave off with is this is very similar to an exponential, but an exponential is a times b to the x. So you can rewrite this as 2 times 1/3 to the x. Noticing it's a y-intercept of 2 and repeatedly multiplying by 1/3, you're going to get 2/3. If you go backwards, you're going to get a 6, and there's your exponential curve. You can make a table. But also don't forget, you can always, even if you didn't recognize the type of function, you can always substitute values in. M of 0 is equal to 1/3 to the 0 times 2. Hopefully we're comfortable and familiar with anything to the 0 power is 1. And so 1 times 2 is equal to 2. And there is 0, 2. You can make a table out of that. M of 1 would equal 1/3 to the first, right? I have an input of 0, so 0 is taking the place of x. I have an input of 1, so 1 is taking the place of x. Or substituting in is the mathematical term there. And so 1/3 times 2 is 2/3. That's this point right there, 1 comma 2/3. M of -1 equals 1/3 to the -1, right? We're taking that -1 is substituted in for x. We talked about earlier, negative exponent means reciprocal, so 3 times 2, or it means division. So what I was dividing by, I'm now multiplying by, is 6. Input of -1 maps to 6. Okay, similar thing with number 6, except again, we want to notice that's linear. There's no variable in the exponent. is being multiplied, and that multiplication is constant additive rate of change. So hopefully that was informative and helpful to anyone who is struggling with linear and exponential functions. I am going to stop this video and I will post it on YouTube soon.